Section 12.4 The factors affecting capacitance. So let's look at this simplest capacitor again. So as you can see, there are two plates of this capacitor. To maximize the capacitance, we put these plates in parallel. The two plates are conductors, and then each plate connects to a wire. We have already known to improve or boost the capacitance, one way is to add a dielectric inside. This dielectric cannot be anything. In other words, not all materials in the universe can be used to boost the capacitance, only some selective materials. Assume the separation distance between the two plates is d. This is the first scenario, so the distance is d1. And now, how about let's separate the plates. This is d2, and then we have the third scenario, d3. The question is, do they have same amount of capacitance? Or which capacitor has most capacitance? The answer is the first type of capacitors, when two plates are close to each other, this kind of capacitor has higher capacitance than the capacitor with plates are far apart. Let's use a very extreme case to analyze. For example, we can put one plate in Los Angeles and the other plate in New York City. The two plates are very far apart. The electrons stored on one plate cannot even interact with the electrons on the other plates because two plates are very far. Those electrons are very far away. So there's no interaction, or we can ignore this interaction. On the other hand, when we place the plates very close to each other, the electrons on one plate can reach and interact with the protons on the other plate. That's why this kind of capacitor has higher capacitance. Based on that analysis, the conclusion is when the plates are very close to each other, bigger capacitance. If the plates are far apart, small capacitance. Let's look at another case. We have a capacitor. Each plate has this amount of area. And now we have another capacitor. Each plate has bigger area. The question is, which capacitor has bigger capacitance and which one has smaller capacitance? The answer is the capacitor with bigger plates has higher capacitance. It's because the capacitor with bigger plates can store more charges. More charges on both plates means more interactions between the protons on one plate and the electrons on the other plates, which means stronger attractions. In conclusion, bigger plate, bigger capacitance. Smaller plate, smaller capacitance. Here has another scenario. The capacitor on the left, two plates are 100% overlapped. And on the right hand side, that capacitor's plates are partially overlapped. Obviously, the capacitor on the left hand side has higher capacitance than the capacitor on the right. The last scenario is when we add the dielectric into the capacitor, the capacitance will be boosted. Most of the time, the capacitance is heavily boosted. To know how much a material can affect the capacitance, we can refer to this table. As you can see, the table has two columns. The first column has the name of the material, and the second column means the relative permittivity. The symbol is epsilon r. The number here means how much is better than a reference material. The reference material we chose is the vacuum, which means all other materials compared to vacuum. For example, let's see, the nylon has a relative permittivity that epsilon r equal to 3.4, which means nylon is 3.4 times better than vacuum. Porcelain has a number 6, which means it's 6 times better than vacuum. Water has a relative permittivity of 80, means using water is 80 times better than using vacuum in terms of boosting the capacitance. Here shows the formula related to dielectric constant. First, dielectric constant, also called relative permittivity, is a number and is dimensionless, which means it has no unit because it's just a relative measure. So the epsilon r, the relative permittivity equals to the actual permittivity epsilon divided by epsilon 0, or also called epsilon naught, which is the permittivity of vacuum. If we rearrange this formula, we get the second one. Epsilon, the actual permittivity of a particular materials, equals to that relative permittivity, which means how much is better, times the permittivity of vacuum, where the permittivity of vacuum, the epsilon 0 equals to 8.85 times 10 to the power negative 12 farad per meter. This is the absolute permittivity of vacuum. Epsilon r is the relative permittivity of a material, which just a number that represents how much times it's better than using vacuum to boost the capacitance of a capacitor. And the epsilon is the absolute permittivity of a material. Now let's look at this double plate capacitor, which is the simplest capacitor. We used the analysis result that we did earlier to get a formula for finding the capacitance of this kind of capacitor. We know the capacitance C related to the dielectric, which is the absolute permittivity of the material, epsilon. It's proportional to the area of the plate. Bigger area, bigger capacitance. Smaller area, smaller capacitance. But it is inverse proportional to the separation distance. The farther the two plates are separated, less capacitance. The closer the plates are apart, more charges can be stored. So it is inverse proportional to the distance. And this is the formula for finding the double plate capacitor's capacitance. Let's work on this example. A double plate capacitor has two square-shaped plates. Both plates have same size, with each side of 2 cm. If both plates are separated by 1 cm, the dielectric material is silicon. What is the capacitance of this capacitor? So we know each plate is a square-shaped plate. We can find the area of a single plate. We know the formula for finding the area of a square is the side times side. So A, the area of the square, is A squared, where A is the length of a single side. Plug in the numbers, equal to 2 centimeter square. However, we need to convert that centimeter to meter, to the SI unit. The reason is, later when we use the permittivity is in the SI unit, is in terms of meter, not centimeter. That's the reason we need to convert this side from 2 centimeter to 2 times 10 to the power negative 2 meter. And if you square the number, it is 4 times 10 to the power negative 4 meter squared. Now let's use that formula. C equals to epsilon A over D. We know epsilon, the absolute permittivity of a material equals to epsilon r, the relative permittivity multiply epsilon naught, which is the permittivity of vacuum, times A over D. Since we are using silicon, silicon has a relative permittivity of 2.5. 2.5 multiplies epsilon 0, the permittivity of vacuum. That is 8.85 times 10 to the power negative 12. The unit is farad per meter. As you can see, this is meter, it is not centimeter. This explains why we need to convert the side from centimeter to meter in step 1. And then multiply the area, the one we calculated already, 4 times 10 to the power negative 4 meter square over the distance. The distance is 1 centimeter, that is 1 times 10 to the power negative 2 meter. And then we're going to punch these numbers into calculator. The result is approximately equal to 8.85 times 10 to the power negative 13 farad. We can convert this number to equivalent engineering notation. That equals to 885.0 times ferrofarad, where the ferro means 10 to the power negative 15.